Alright, now we're going to look at what we call descriptive limits. So in some of the instances before where we've said a limit does not exist, we can actually refine that, and we can use what we call a descriptive limit instead of just saying that it doesn't exist. Now technically it still does not exist, but the descriptive limit is more useful because it's more descriptive. Weird. Alright, so I want you to take a minute and identify the following limits here. Pause the video, unpause when you're ready to check for work. Okay, so what's happening here, you might have written does not exist for all of these, but actually a lot of them we can give descriptive limits now. Descriptive, that's a V, limits. And actually I'll do that. So what we're doing is we're describing the behavior of the graph. And this really only is going to come into play when the graph is going to infinity or negative infinity. And remember, what we're saying is as the y values go towards negative infinity or infinity, which is going to happen when we approach a vertical asymptote. So I know, because I understand rational functions, that at -2 on these functions, there is a vertical asymptote. So I know that I am not going to approach a single value, so by definition, by my limit definition, the limit does not exist. However, for a one-sided limit especially, I can actually look and I can either use my calculator. So here in y1, I plugged in 1 over x plus 2 squared, and in y2, I plugged in 1 over x plus 2. And if I look at the table, it's easier to see. So as x goes to 2, or I'm sorry, as x goes to -2 from the right, so that's these values, here's my y1 and here's my y2, notice that the y values are getting very, very large, very, very quickly. When that happens, that doesn't mean I'm approaching a number, that means I'm going to infinity. And remember, we know that because we graphed many rational functions first semester. We know that as a function approaches a vertical asymptote, it's going to either shoot up to infinity or it's going to shoot down to negative infinity. I can also see that if I actually look at the graphs, but remember, graphs aren't terribly useful. So it's a little bit hard to tell because I have both graphs going on at once, but the 1 over x plus 2 squared is both pieces going up, and the 1 over x plus 2 has the one piece going to negative infinity and the other piece going to positive infinity. So that's how I get my descriptive limits, is I'm describing what is the graph doing as it approaches the vertical asymptote. So here it's approaching infinity from the right, it's approaching infinity from the left, therefore from the left and the right it's approaching infinity. Here from the right it's approaching infinity, from the left it's approaching negative infinity, therefore from the left and the right the function or the limit does not exist because it's not, I can't describe it using one thing. So now from here on out, anytime we have this situation where we're evaluating the limit at a vertical asymptote, you want to use a descriptive limit if it exists, if the descriptive limit exists. Remember, technically the limit does not, but we can use a descriptive limit. So, vertical asymptotes again. So if f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. Remember, that is, we have vertical asymptotes as more functions than just rational functions. We saw them in logs right at the very end of first semester as an example. Another definition is let f and g be continuous on an open interval containing c, where f of c does not equal 0 and g of c does equal 0, and there exists an open interval containing c such that g of x does not equal 0 for all x does not equal c in the interval. Then the graph of the function given by h of x equals f of x over g of x has a vertical asymptote at x equals c. This is a really long-winded way of saying if we have a rational function and the denominator equals 0 but the numerator does not, then we have a vertical asymptote. Alright, I want you to find all the vertical asymptotes in this function. Pause the video, unpause when you're ready to check. Alright, hopefully you got that the vertical asymptotes are at x equals 0 and x equals 3. How do we get that? We do a lot of factoring. So I factored out a greatest common factor from the numerator and denominator, then I factored the denominator by grouping. I did that off to the side up here. And then I saw that, okay, I have a common factor of x plus 3. That's actually going to be a whole. a common factor of x minus 2, also a whole, and so I'm left with x and x minus 3 in the denominator, so that's where I'm going to get my vertical asymptotes of x equals 0 and x equals positive 3. Alright, so I want you to try these on your own. You can use your calculator, but I want you to try and think about how to do this without your calculator, and really it comes down to just kind of thinking about it, because the answer is going to be descriptive limits for these. So pause the video, try these, unpause when you're ready to check. Alright, so the first one here, I end up with a descriptive limit of negative infinity. So how do I come up with that? This is the thought process that you want to go through. Okay, what's happening at x equals 1? There's a vertical asymptote. I know that because if I plug in 1, I'm actually going to get 3 over 0. That tells me vertical asymptote. Okay, so I could put this in my calculator and I could look at the table or a graph, but what if I don't have a calculator, right? What if my batteries die, right? What if I got upset and I broke it? What if my friend stole it? What if worse? What if my brother or sister stole it? Oh, sister. Anyway, so what I'm going to do is I'm going to plug in a number that's a little bit to the right of 1. What I'm looking for is, okay, if there is a vertical asymptote at x equals 1, then, and because this is a one-sided limit, if it's a two-sided limit, I got to check both sides. But because it's a one-sided limit, I know that the descriptive limit is going to exist. It has to. If there's a vertical asymptote there and it's a one-sided limit, there will be a descriptive limit because a function always approaches infinity or negative infinity from a single side as it approaches a vertical asymptote. So if I plug in something a little bit to the right of 1, all I really care about is the function positive or negative, because that's going to tell me which infinity value it's going to. So if I plug in this case 1.01, yeah, I know that 2 plus 1.01 is 3.01, but I don't care about the value. I just care that that's going to become a positive sum. 1 minus 1.01 is a negative sum. If I divide a positive by a negative, I'm going to get a negative as a result. So therefore this has to be going to negative infinity. You could actually find these numbers. You could look at, okay, what's going to happen if I plug in 1.001 in the numerator and denominator, and I'll see it's still positive over negative. And that pattern's going to continue. It's just the numbers are going to become larger and larger, but they're going to stay negative. So therefore I know it's going to negative infinity. On this one here, I know there's a vertical asymptote at x equals 0. So actually what I did was I split this up into two separate limits. The limit as x goes to 0 from the left of x squared is just 0. So then this one though, the limit as x goes to 0 from the left of 1 over x, now again, I want to plug in something just a little bit to the left of 0. And what I'm looking for is this going towards the positive direction or the negative direction. Well, the numerator is just always positive, so if I plug in a negative in the denominator, it's negative. So now I have 0 minus a positive over a negative, but if I divide a positive by a negative, that actually gives me a negative. So I have 0 minus a negative, which actually becomes positive. So therefore, the limit as x goes to 0 from the left of x squared minus 1 over x is positive infinity. I do want to also point out, again, the notation here is mathematically sound. I am not saying that a positive over a negative equals infinity or negative infinity. So that's why I'm doing vertical work. I'm not just writing a bunch of equal signs. Moving on. Alright, properties of limits with descriptive limits. So if we have c and l be real numbers and f and g be functions such that the limit as x goes to c of f of x equals infinity and the limit as x goes to c of g of x equals l. Well, what happens if we add or subtract them? The limit as x goes to c of f of x plus or minus g of x is going to equal infinity. Because if I add or subtract a constant, it doesn't matter. Infinity plus or minus a number is still infinity. What if I multiply? So f of x times g of x is going to equal infinity if the limit of g of x was positive, and it's going to equal negative infinity if the limit of g of x was negative. What if I divide? The limit as x goes to c of g of x over f of x is going to equal 0. So what that's saying is if I just take a number divided by infinity, that is going to equal 0 because that's what it's going to approach. All right, evaluate these two limits. Pause the video. Unpause when you're ready to check. All right, for the first one here, don't get so caught up in all these descriptive limits. Just try direct substitution, and we get 0 over 3, which is 0. Right? So, we've seen all these other techniques. Yeah, you can factor the numerator, but we don't have to. Remember, always just try direct substitution first, if you didn't. For the next one, though, we do have to do a descriptive limit. I know that there's a vertical asymptote at x equals 3, so I know that 3 is going to be a problem, so I can't do direct substitution. But since I want to check 3 from the right, I can think about, well, what if I plug in something a little bit to the right? So 6 minus 3.01 is a positive number, and the square root of 3.01 minus 3 is also a positive number. Positive divided by positive is always going to go to positive infinity. Next, now we have an application problem. So the cost in dollars of removing P% of the air pollutants from the stack emission of a utility company that burns coal to generate electricity is this function, where P is between 0 and 100 because it's a percent. Find the cost of removing 90% of the coal, and then I want you to find the limit of C as P goes to 100 from the left and interpret its meaning in the context of the problem. I know, you love those. Pause the video. Do that. Unpause when you're ready to check. Alright, hopefully the first one is pretty straightforward. You just plug in 90. So 80,000 times 90 over 100 minus 90, and we get 720,000. So the cost of removing 90% of pollutants is $720,000. So then what about the limit? The limit as P goes to 100 from the left of the function C. Well, I know that at 100 is a vertical asymptote, so I did plug in something a little bit to the left, and I get positive divided by positive. That means I'm going to infinity. So the cost of trying to remove all pollutants will become infinitely large. That's going to be the interpretation in the context of the problem. That's pretty gloomy. So, last one. I want you to find two functions, f and g, such that the limit as x goes to c of f of x is infinity, and the limit as x goes to c of g of x is also infinity, but the limit as x goes to c of f of x minus g of x is not infinity. I'm sorry, this is not 0. I apologize. There are many correct answers. Pause the video, do this, unpause when you're ready to discuss. Alright, so I came up with f of x equals 1 over x squared and g of x equals 1 over x to the fourth. Again, there are other options. So I said the limit as x goes to 0 of 1 over x squared is infinity. The limit as x goes to 0 of 1 over x to the fourth is infinity. But if I do the limit as x goes to 0 of the difference between the two, I actually get negative infinity. I can show you this on the calculator. So I put the functions in. So y1 is 1 over x squared, y2 is 1 over x to the fourth, and y3 is y1 minus y2. If I look at the table, I can see that both the first function and the second function approach infinity from the left and the right. And then if I go over to y3, I can see that this approaches negative infinity from the left and the right. You can see this graphically as well. It's a little bit harder to tell, I guess. So y1 and y2 are both going up, but y3 is going down. It's going down. Alright, so if the evaluation of a limit results in positive or negative infinity, that is called a descriptive limit. The actual limit technically does not exist, but now we will use the descriptive limit if we can. Vertical asymptotes can lead to limits to infinity, which is just a descriptive limit.